Okay, it's time to put all of this work we've been doing with conditional statements and deductive reasoning and logic all together into what is called a formal proof, where we're going to use facts and justifications to put together proof that our conclusions are true. And so one way that we can write a proof is to do a two-column format. A two-column proof has certain parts that we need to understand. First of all, there's usually some kind of a diagram given to you, and you'll want to write those diagrams out if you're copying them out of the book. Also, there's what's called the given statement. And the given statement comes directly from the hypothesis of our statement that we're trying to prove. So it's the stuff that we get to start just assuming those things are true. Then there's always something that we're going to be trying to prove, which is the conclusion of our if-then statements. So we're going to use our deductive reasoning to show that if our hypothesis is true, along with all the other facts that we know, then the conclusion must be true. And then we lay it out in this kind of a format. This is called a two-column proof because the statements that we give are written in the first column, and the justifications or the reasons that we give are written in the second column. Again, these also could be labeled reasons. So every statement we make, we back it up with a justification. And you don't have to number them, but usually there's some kind of a numbering system so that everybody can refer to which line in the proof you might be talking about. So let's take a look at this first example. You see here we've got our diagram laid out. And we've got a given statement about the diagram. Let's read that. It's AB is the bisector of angle CAD. So here we find ray AB coming through angle CAD as a bisector, cutting it in half. Our job is to prove that the value of x is 9. So we have to work from the given to the conclusion. So in our columns, we see the statements listed here and the reasons listed here, and some of these are blank, and we're going to be filling these in. First, we read that AB is the bisector of CAD. Well, how do we know that? Our reason for that is just because it was a given statement. That's what we got to start with. The given statement is always a true statement. Now, if AB is the bisector of angle CAD, what else can we conclude? Our next statement says that angle CAB is congruent to angle BAD. So in our diagram, CAB is this angle here, and BAD is this angle here. The claim is that they are congruent angles. So if I tick mark them, that's what this second statement is saying. How do we know that those are congruent angles? What tells us this matches this? Well, the reason is back up in the first statement. We were told there was a bisector there. So because it's a bisector, the definition of bisector cuts it in half. So our justification is definition of bisector. Now, when we read on, the next statement talks about the measure of angle CAB and that it matches or is equal to, well, that should say equal to, I need to change that in the note packet. That should say equal to BAD. So this angle measure equals this angle measure. And that's simply because they were congruent angles, and congruent angles have the equal measures. Sometimes you would leave this line out and go straight to the next line. 7x plus 2 is equal to 5 times the quantity of x plus 4. How do we know that? Well, we've solved these kinds of equations before. We've taken the expressions in the picture and basically put them into the relationship we just said, that the measures are equal. So that's a substitution. We made a replacement. Instead of talking about the angles themselves, we're talking about the measures now. We're substituting the values in. Okay, reading on. How does this line then change into this line? Well, the left side of the equation didn't change at all, but the right side, it looks like the 5 has been multiplied through the parentheses. 5 times x is 5x, and 5 times 4 is 20. You might remember that's the distributive property, and that is our justification, distributive property. All right, now what would be the next step in solving this? If I were going to solve this, I would start moving things across the equal sign. First thing, I would subtract that 5x there. If I subtract 5x from this side, and I subtract 5x from this side, that 7x becomes a 2x. If I also subtract the 2 from both sides. That would cancel it from the left, and over on the right I'd have 20 subtract 2 to give me 2x equals 18. So what happened on both parts of that? It was the subtraction property. Then the last step of this is to get it down to say just 1x. So I'm going to divide both sides by 2. And dividing that by 2 will give me just 1x, and dividing 18 by 2 will give me 9. And that was the division property that I used. And that's also what I was trying to prove. So x equals 9. Followed by all of those steps, we got to the point that x is equal to 9. Okay, so here's my next problem. We're going to write a two-column proof to prove the statement is true. So basically, we have the statement, if 5x minus 9 is equal to 16x plus 6, there's my hypothesis, then my conclusion is x is equal to negative 15/11. So essentially, this is like an algebra problem that I'm already giving you the answer to, and you're just going to justify every step along the way. So in our two-column proof, we always write down what's given to us. Again, that's always the hypothesis, so that's going to be the 5x minus 9 equals 16x plus 6. And we're going to prove in the end that starting with that is going to lead us to x is equal to negative 15/11. Now there's not a diagram for this one, but over here I am going to use a little bit of scratch work so that I can talk myself through this. In fact, let's just start solving this equation, and we'll write out and justify our steps here. So let's set up our two columns. And here we're going to start out with our first information, which is 5x minus 9 is equal to 16x plus 6. And we know that just because that's our given statement. Now, if I'm solving this equation over here, the first thing I would be doing to this is I would be subtracting off the 5x's and subtracting them from both sides to cancel them here. And I would also be subtracting the 6 to cancel that from the right side. And then I would get my new total. So my new total is negative 15 on the left, and this comes to 11x on the right. So that's my next line. My next result is negative 15 is equal to 11x. And how did I get that? I did the subtraction property. All right, back to my little thought bubble over here. Now I'm going to get x alone by doing a divide by 11 on both sides. So that brings me to 11, or sorry, that brings me to those canceling. That's 1x. And over on this side, I get negative 15/11. So that's my next step. That can be changed into negative 15/11 is equal to x. And the step we took was right here. We did this division right here. So this is division property. Okay, almost done. X is alone, but when I look back at what my goal was, I wanted to have x on the left. So I need to switch these around. And so I'm going to put x in the front and that equal 11 and let it equal negative 15/11. What allows me to do that? Well, you might remember that's that symmetric property, that the left or right side is the same, symmetric property. Just like the left and right sides of your face are the same, the left and right sides of the equation can be switched around. Symmetric property. Okay. All right, so there's one on here for you to try. Let's read through what's given and what you're going to prove. You're given the distance from K to L. If you look at your picture with the diagram all the way from K to L, this segment is 3 times the length of PM. So K to L is 3 times longer than this shorter segment PM. Your job is to prove formally that x is equal to 12. So here's all the statements going through, and your job again is to justify the reason for every statement that is made. Good luck with that, and we'll talk about it again.